Hey, welcome back to Fat Mama Physics. In this video, we are going to do a multi-loop circuit, one of the harder problems you'll see in analyzing circuits. So here I have an example in which we will try to analyze. These little boxes here are resistors, just different ways to show that. And what do we want to do? We want to calculate the current in each resistor in the circuit shown on the right. Okay, well, yes, very tricky problem. Okay, so before we begin I'm just going to want to simplify whatever here I can simplify. The first thing I'm going to try to simplify here is just combining these two resistors, which we know, since they're in series, we can just put them together. We can combine them in series, which we just add 2 plus 3 ohms, giving us just the one resistor here, which I'm just going to call this resistor A with 5 ohms, just to make it easier for us to solve this circuit. Okay. So the first thing, whenever you get a complicated circuit, is I try to look at the direction of the current. I'm going to try to break that up, and just to see what's going on. So I'm going to make it an initial assumption on the direction of every current across every resistor. And when I do my calculations, if I calculate the current to be negative, I know that the current must be in the opposite direction. So I don't really care. It doesn't really matter if we get the direction of the current wrong now, okay? As long as we are consistent with our analysis. So what to do first? Number one is I'm going to start at one battery. I'm going to assume what's happening here. Let's start at this battery here. And let's say the current goes in this direction. And I'm just going to call this current here I1. As this current goes around, it meets a junction, and we know for currents will split off. So this is going to split off here, in which I'm going to call this, let's say I3, and I'll call this current going through this battery I2. So notice that every point where my current splits up, or it goes into a different pathway, I name a different current because we know those currents are not going to be the same. So this guy goes along, they meet up here again, so this current goes through RA, this resistor, they meet up here again, and then they combine to form I1 again. So that's the first thing that I do when I get a complicated circuit. Now we can use Kirchhoff's laws to write us a bunch of equations, because through all these equations we can probably figure out a few variables. We could solve for a few variables, and maybe when it does get complicated you might have to do systems of equations where we need to substitute numbers from variables from one equation to another. I don't think it's the case for this one, so we might luck off. But let's start off with writing our initial equations. Based off of my initial assumptions, my current 1 gets split up to current 2 and current 3. So that in itself, one equation right there. I2 is going to be equal to I1 is going to be equal to I2 plus I3 combined together. The next set of equations, which are going to be dependent on Kirchhoff's laws, are going to what we're going to do is we're going to look at every loop. The idea is, if we go around every loop, the total potential difference should equal 0. If I go around this loop, the sum of the potential gains and drops are going to give me 0. If I go around the top loop, that's going to be 0 as well. If I go around this whole loop on the outside, the total potential difference or the total potential drop is going to be 0, because we're going to add up all the gains, subtract the losses, and that should give us a net potential difference of 0. So that's the key thing before we write the next set of equations, because we not only have this loop, we have this loop, and we have this loop on the outside, all going around in a big circle. So we should have 3 equations for each loop, okay? So if things all work out, technically there could have been 4 unknowns in this entire circuit, and we should be able to figure them all out with 4 equations. Okay, you might think that, oh, well, hey, look here, the potential difference here is 3 volts, which means it should be exactly 3 volts across this bottom resistor, and we know from Ohm's law that the potential drop, or V, is equal to IR, and since for something in parallel, since these 2 points are in parallel with this resistor here, then 3 volts is equal to that current on the bottom, which is going to be I3, times this resistor, which is going to be the 5 ohms, then, oh, that was ugly, then we should get a current down on the bottom of 3 divided by 5, which is going to be 0.6, oh, sorry, no bar, 0.6 amps, okay? That's a quick, dirty way to get you started, for sure. But take a look. We want to figure out the current, calculate the current in each resistor in the circuit shown on the right. Oh, okay. Oh, well, okay, I guess the answer key only gives us the top loop and the bottom loop, which is I1 and I2. So I3 was probably the easiest to figure out, which is probably why it's not there in the key. But let's take a look. I'm going to use a different color for every loop. So I'm going to start with the black loop, which is the big loop all on the outside. So on the outside, I'm going to start off with a battery. Always good to start off with a battery. We know that the sum is going to give us 0 potential. The net potential is going to be 0. So the battery is going to, if I follow the direction of my current, this is going to give me a jump of 9 volts. I think of steps. I go up 9 steps up the ladder or something. So that's like 9 steps up. So that's like that's going to be positive. If I go across a resistor, I'm going to come down. My potential is going to drop. So I'm going to subtract, and I know that the potential for a battery is just going to be V equals to IR, Ohm's law. So that's going to be I times R, because I don't know what that potential drop across that battery is. So IR for that battery, IR radiation, just kidding. It's going to be I1 times R1, and R1 is just going to be 4 ohms. Okay, as I go along this outside, then the next drop here is going to be across these 2 resistors, which I've combined into the RA into one huge resistor. I can just color it in so it may be easy to see. So that's just going to be, assuming the current for I3 is going down, I will subtract I3 times the 5 ohms down here on the bottom, and the current goes across and backs and all the way back to my initial battery over there. So that's my first loop. Let's go through another loop. Let's do this top loop here. I'll do it in blue, okay? So this top loop, again, my total voltage drop is going to be 0. And again, let's start at a battery. Let's start off with this 9-volt battery because it seems like it's stronger than the other one. So with a 9-volt battery, again, it's going to be a positive gain. I'm going up the ladder. And then again, I'm going to drop across that first resistor there. So that's I1, which we don't know what it is right now. And what's going to happen is this guy's going to loop around and it's going to come down. But it's going to be I2 that is going over this next battery here. And this is also a step up, basically. So it's a step up, which means I'm going to have to add this voltage, add it as a voltage gain, assuming that I2 is in the correct direction. And then this goes all the way back to my original battery. So that's my next loop. My final loop is going to be this one that's down here, which I'm going to use purple instead. And again, I'm going to start off at a battery because a battery is just an easy way to go. So at the 3-volt battery here, I get a step up, okay? I get a step up, which is going to be 3 volts. And as I'm going down to the bottom, notice we come across a problem. The problem is that I3 technically goes up in this direction But if I want to move through this loop, I am going against the current. If I'm going against the current, or based off of the current that I assumed, this is no longer a potential drop. In fact, this will be a potential gain if I go across this resistor, because I am going against the current. So I would have to write this as not minus IR, because I'm going against the current, I'm going up the ladder through this resistor. So that's going to be adding I3 times the 5 ohm resistor. Okay, I know that's one weird thing about analyzing circuits is, especially when you go against the current. If you go against the current, especially for a resistor, that means you would have to go up the potential instead. So I would add it before I come all the way back to this battery. Already you're thinking, well, how does that work? There's no way for my net potential difference to be 0 if I'm just adding all of them, right? Well then, this is where problems start to arise, which is okay. Remember I said at the beginning that if you get the current to be negative, then it just means that our initial assumptions were wrong. My initial assumptions were wrong. The current must have been going the opposite direction, which we will see in a second. So, since we've been talking about that, let's do that right now. I'm going to isolate these two on both sides of the equation. So I'm going to move, let's move this guy to the other side. So I'm going to get 3 volts, which I am just going to, I'm going to forego all the units. I'm just going to write numbers, so in the end we can get some numbers. So 3 is going to be equal to negative I3 times 5, or actually 5 times I3. Okay, 5 times I3, okay? There you go. So that means if I solve for I3 is going to be 3 divided by 5. Don't forget that negative sign, and that's going to be negative 0.6 amps. And what that negative means is that my initial assumption of the direction of the current is incorrect. It should be in the opposite direction. But notice that this way of calculating for the current, I not only get my value, which we did earlier, but I also get the direction of the current, or it helps me correct for the direction of my current. So let's go back to my my diagram here, in which the red for the I3 is going to be wrong. So I'm going to have to get rid of this. Oopsie, that's too much. I'm going to have to erase this arrow over here, and based off of my new findings, let's connect this back here again. My new findings tell me that I3 should go opposite, so not counterclockwise, but it should go clockwise, this direction, through the resistor and back over here. So I3 goes this way. Okay, I3 goes this way. And what we can do now is, well, we could just say the magnitude here is 0.6 amps, and that will be that. But we can go back and just double check all the other I3s that we've assumed in the other loop equations. So the blue loop is clean, so we don't need to worry about that one. But we probably need to worry about the black one, which is a full loop around. So, what that means is we can still make that loop around, except that even though we're going against the current, it's fine. All we have to do is just flip the sign to know that we are going up the current. Or, sorry, going against the current for that matter. So let's just go back and trace this again. The 9 volts was due to our increase in potential, and the next one was a decrease in potential because it's going across a resistor. But as it goes down, we are now going against I3's current. Going against I3's current means that this is going to be adding instead of subtracting. We're going to add this potential as a potential gain of this resistor, and then that's going to lead us back to the battery again. So after we add that plus sign, everything else in this loop equation should now make sense, because it should give us a net value of 0. Guess what? Let's check that right now just to confirm. I'm going to go scroll down and rewrite this again, which is 0 equals to 9. I'm going to get rid of all the units, so that way we can see the numbers quite clearly. This is going to be 4I1 plus 5i3. Okay, so we actually know what i3 is. We've also confirmed it twice. So in fact, what we should be solving for in this case is I1, which we don't know. So let's just put I1 on one side of the equation, or you know what? Yes, let's do that. Okay, so if I put I1, so let's move I1 over here, with the 4, of course. So we get 4I1 equals to 9 plus 5 times I3. Okay, we know what I3 is. I3 is 0.6 amps, as we found earlier. That's the bottom loop. So after we substitute this in, we get 9 plus 5 times 0.6 amps, which is going to be equal to 9 plus 3, which is 12 volts. Okay, so with a total of 12 volts, we just have to divide both sides by 4 to give us I1 is equal to 3 amps. Okay, with sig figs is probably like 3.0 amps or something. Okay, hey, we got I1. Let's see if it makes sense. Okay, let's see if everything makes sense based off the direction of our currents and everything. I1 is 3 amps. Okay, did I say I3? I1. I1 is 3 amps. I3 is 6 amps. Okay, so let's see if everything adds up. So I1 goes here, and that's going to combine with I3 coming in, which means I2 should be equal to the sum of I1 and I3, which is 3 plus 0.6. So I2 should give us 3.6 amps if we add these two together. That's the idea here, because we know from, you know what? Nice catch. I totally forgot about our first equation, which is the assumption about our currents. Okay? So because of the direction, we found out I3 was in the opposite direction. We know that I3 plus I1 together is going to give us I2. So this is wrong. It should be I2. I2 is the sum of I1 plus I3, because these two currents combine together to give us I2, which is 3 plus 0.6. This is 3.6 amps. Okay? Well, you know what? You might be a little bit doubtful of this one right now, but we can confirm this. Why don't we confirm this with the blue loop, okay? The blue loop is, let's write the equation over here, is going to be 0 is equal to 9 minus 4 times I1 plus 3. I've just taken out all the units, so we can just see this nice and clearly. So we know that 9 plus 3 is 12, okay? So that's 12. And I'm going to move that, actually, I'm going to keep that, but I'm going to move this to the other side of the equation, which is going to be, which will turn that into a positive. That's going to be 4i, okay? So with that, the I is going to be, divide both sides by 4, just like what we did before, which is going to be 3 amps. So notice that all 4 equations confirm that the current in I1 is 3, and which means if that is true, and if I3 is correct, then I2 must be 3.6 amps. Okay? So guess what? We just solved for all the currents in this question. So the top loop is going to be 3 amps, the middle loop is going to be 3.6 amps, and not shown here in the question, the bottom loop will be 0.6 amps. Okay? So takeaways. In a multi-loop circuit, the first thing you want to do is, of course, simplify it as much as you can, but then you want to make an assumption of where the current is going, draw out all of your current diagrams, label them correctly, then you can write down all of your equations. You get one equation for the sum of the current. You get one equation each for every loop that you have in your circuitry. Every loop, the net potential difference should sum up to 0. So that should give you one equation per loop. After you have those equations, then you can go ahead and solve for each current through every loop. So hopefully this tough problem was broken down enough for you that you hopefully get a better understanding of how it works. I highly encourage you to try another example on your own, applying everything you learned in this question. I thank you for watching. I wish you good luck, and Fat Mama Physics signing out.